All right, so the last class we were discussing about the maneuvering models, and we understood the idea that the governing equations that we had wrote down for the rigid body kinetics, and but we were wanting to now include uh, some of the forces which are categorized in this tau. We want to extract them out, and we want to give an explicit dynamics to be modeled in our system dynamics. So the idea was primarily we wanted to look at how the hydrodynamic forces and added mass and radiation damping play a picture, and how do I incorporate them, or how do I model them in order to get a complete maneuvering system. The idea there was that we initially looked at horizontal modes, as we will be looking from time to time. So you kind of see me switch back from a 6 degree of freedom system to a 3 degree of freedom system fairly often, because when we are dealing with dynamic positioning or so-called DP operations, we'll see that most of the time the interest is to see if we can control these horizontal modes of action. So how do I orient my surge, sway, and yaw? So can I maintain a certain position and an orientation over certain time over which some dynamic operation might be happening? So you may think of a typical example as, let's say that there is an offshore structure, okay, and I want to install the top side of the offshore structure. So the hull of the offshore structure is in place, but we want to install the top side of the offshore structure onto the vessel. So there, where you are lifting the entire top side off by huge cranes and trying to place it on top of a floating offshore structure, you need to make sure that the crane is not moving relative, or at least the end point of the crane is not moving relative to the structure on which you are placing it. Is that making sense? Yes. So suppose I have a semi-submersible platform. So the semi-submersible is floating, but the top side of that platform, on which you generally have the oil rig, the processing plant, the storage facility, all of those are there on what is called as the top side of the facility, right? So if I were to take a look, let's see here. So you typically have, so if I see, let's say I have some pontoon and then columns, and then this is my draft, and this thing is floating. Now on top of this, there will be a top side which will be installed, on which you, let's say you have the drilling rig. Okay, so from where you're actually drilling, lowering a drill string onto the seabed. In most cases, this is not a drilling rig, it's a production platform, so these are mostly risers. Okay, and then you'll have mooring lines which are connecting to the hull and mooring it down. So these would be something like steel catenary risers. Right? And then you'll have other systems in place on the top side, which will be handling what happens to the crude oil when it comes up, how does it get processed, how does it get stored, and so on and so forth. All those machinery, equipment, which is required for the handling on the so-called extraction of the crude oil once it starts flowing out, all that will be there on what is this thing called as the top side. Top side of the platform. So typically you will not construct this as a single piece. You will construct the semi-submersible separately, you will float it in, and then you'll tug it in here. So which means that there will be tugboats which will be pulling it and then bringing it to the site location. And then on top of that, you have to install this top side so that the drilling rig or the so-called production platform becomes operational. Is everybody with me so far?
Yes, sir.
Okay. So when I have to install this top side, generally what happens is that there will be a huge crane. So there will be huge cranes. And these will be really large cranes. Okay. And they'll be holding on to these this one and then lifting it, and there will be multiple cranes in general. We'll see 3 or 4 cranes might be lifting it up. So you want this, as you're lowering this top side down onto the platform, this thing, because there are waves in the ocean, the structure itself will be moving up and down, or it will be doing little surge and sway, and then sometimes even a yaw, right? So typically you'll see there will be a surge, sway, and yaw. Now you need to compensate for all these 3 motions in order to make sure that the top side can be directly lowered onto the correct position. Is that making sense? Yes. So the idea here is that as I am lowering it, there should not be a relative motion between the column here, let's say the latching point here, and the top side matching point, which I want to match it on that position. So I should be able to lower it without having to execute. These 2 points, the relative motion should be low. Only then I can peacefully put it down, right? Otherwise, I can't guarantee that I'll put it down at the position where I want it to be put down. Is that making sense?
Yes.
Yes? Right. So when we want to do such operations, so these are typical dynamic positioning operations. So these are the typical DP operations, or short as DP. And one has to make sure that the winch of the crane, of the so-called, let's say, the winch on the crane, as I am lowering it or pulling it back up, I need to do it in such a manner. I need to do that in a controlled manner so that there is no relative motion between these 2 points. Another example might be like when I have to offload cargo. Let's say that I have a huge bulk carrier which is carrying, let's say, some amount of, I don't know, okay, and there's a crane on top which is trying to have a hooper to try to pull out that and offload it onto another vessel which has come closer. So these are another operations which you typically see. So you don't want to see that when the crane is putting it down on the other ship, there to be a relative motion. Similarly, you may have in a dynamic positioning operations, you may have an offshore platform which is operating, and then there may be a ship which might have come to offload some of that things which it has been taking on. And at certain times, you may want to transfer some machinery or equipment for maintenance purposes from the offshore supply vessels over to the top sides. So when you want to do that, you want to make sure that the crane which is trying to lift this up is doing it such a manner that there is no relative motion at the time of picking up. So just imagine that if these waves are really huge, if you're operating, let's say, in somewhere in sea states 5 or 6, which is typical in the North Atlantic region, then you are experiencing, both the platforms are experiencing significant motion, and one has to really figure out a way where I can take a load from one platform and lower it onto the other platform while trying to minimize my motion. What happens if I don't minimize? I'll be trying to either slam the load on the deck, I mean, deform the deck. I may be able to, what you call, damage the machinery that I want to lower. So it is important to make sure that these operations happen in a smooth manner. So for that, a significant amount of understanding is required. Similarly, when this vessel is floating here and we are trying to lift something off of that vessel, you have to make sure that this vessel maintains its position. And sometimes not just the position, you also want the orientation to be maintained, so that the crane operator can then specifically plan to pick out an item which is on your deck and transfer it onto the top side. Is that making sense? Yeah. So for these purposes, it is very important to maintain the horizontal position and orientation of the craft, which is why you'll see many times when we are looking at DP operations, we are restricting ourselves to the so-called horizontal modes, because the wave loads we can't really avoid. We know that there will be some heave, some pitch, and some roll, but typically in a ocean they will be smaller in number. So you won't see pitch by 10 degrees or 20 degrees. Similarly, roll you will not see by a huge amount if you have designed the vessel well. Whereas in the surge, sway, and yaw, it's a different story. Because there is no stiffness in the surge, sway, and yaw, maintaining position in it is difficult. So you need an active control in order to do the maintaining of the position in the horizontal modes of motion. So that is what dynamic positioning usually deals with. So you will often see that even though we have derived the equations of motion in 6 degrees of freedom, many a times we'll be interested in the so-called horizontal modes of motion. And for that, we saw that the equations can be simplified a little bit, especially by choosing the origin, the coordinate origin, on a symmetric exit plane, which is typically possible for most ships because ships have a center line based symmetry. So in which case you can reduce these nonlinear equations into a 3 degree of freedom system for a 3 degree of freedom system. We also looked at the idea that you can make a linear approximation of them, and I'm now going to go over this again. We covered this last time. And then we understood that there is an added mass and a radiation damping which must be accounted for when we are dealing with ocean vessels floating in the ocean. And the idea was that this added mass is generally going to be related to the so-called zero frequency, so that we are looking at very slow operations. And it is understood that although the motions in heave, pitch, and roll are significantly matching with the periods of the waves, or close to the natural frequencies are pretty, or the natural periods in these three modes are quite high. On the horizontal mode, since the lack of stiffness, you will see that the time period of these modes is much slower. So it's a good approximation to take a zero frequency case and figure out what are the added masses and radiation damping. Now, I also told you that for most operations, this damping matrix will be zeros, which comes primarily from the potential damping. So if you're looking at anything which is coming from the potential damping, these values will be zeros. So that's why you will need to consider viscous effects when modeling these vessels. So the viscous effects will become important, and you will need to figure out a way to estimate these viscous forces, or at least estimate them in to some degree of approximation. We looked at the idea that in this case, if we wanted to include the other 3 degrees of freedom, then we are looking at an added mass matrix, which is composed of zero frequency terms for the surge, sway, and yaw. But for the heave, pitch, and roll, we generally have them computed at their natural frequencies of the decoupled heave, roll, and pitch. Similarly, the damping also can be modeled at that location. And this is where we left off at the last class. Okay, Any questions so far? No questions? All right, so let us proceed further. Now, so when I include that so-called added mass into my system, what I'll see is that the dynamic equations of motion can now be written as this large equation which you see here. Here I'm separating out a couple of different things. So let's talk term by term what's happening. So MRB is the rigid body mass matrix which we had before. Now, in addition to that, we have an additional mass matrix. This is the added mass matrix. Now, remember we had the Coriolis matrix with respect to the rigid body. Now we'll also have a Coriolis matrix corresponding to the added mass. Is that making sense so far?
Yes, sir.
Okay. Now, in addition to that, we'll also have dissipating damping forces. So as I said, we have to take into account viscous effects and other things. So those will be damping forces. So that matrix will be taken as d of v times v. Notice that as long as it is depending on v, this is a nonlinear formulation. In some cases where the nonlinear terms are not so important, you may be able to get away with a linear approximation of this, but typically for most of the dynamic positioning applications, you will need to incorporate the nonlinear damping into the system. We'll talk about what are the different nonlinear damping models which we are available to us and how those modelings, what are the different models which we can formulate, maneuvering models which we can formulate using these different damping models. Then the next term here is a vector, so g of eta, so where eta is the state vector, and this is the so-called generalized hydrostatic forces. Notice that the first two and the last value of this vector will typically be zeros because you will not have any hydrostatics come into the picture when you're looking at surge, sway, and yaw. But if you're looking at a underwater vehicle, that would not be the case. So depending on where the center of buoyancy is and where the center of gravity is, and as you ballast the vehicle, how does the center of buoyancy shift or center of gravity shift will cause some generalized hydrostatic forces to come into the picture. Now, for our purposes, for most case, we will be focusing our efforts on surface vessels. So we'll primarily be looking at this vector will only be important when we want to include the sea-keeping modes along with the maneuvering modes. If you are only looking at the surge, sway, and the yaw, you'll typically find that this vector will not be there in our equations of motion. Am I making sense here?
Yes, sir.
Sir, can you repeat this part?
Yes. So the idea is simple. There is no stiffness in surge, sway, and yaw, right? We don't even experience any stiffness force. Right? So if we are looking at a 3 degree of freedom model, then this term will typically be not there. It will be basically all zeros, right?
Okay, the hydrostatic forces, right?
Hydrostatic forces will be zero.
Yes.
But suppose if I wanted to include roll also as a mode, so say I'm looking at a 4 degree of freedom model, then I can't ignore the hydrostatics in the roll, and that part has to be captured in this vector.
Yes.
Okay. So for most of our applications, when we are dealing with surface vessels, this part will not be important. But if we are looking at underwater vehicles, then this part does become important because when we change the ballasts or when we change the buoyancy, we are actually going to experience a change in the net forcing on the vehicle, the net hydrostatic forcing on the vehicle, including the mass. So those effects are actually captured here.
Yes, sir. Yes.
Okay. But for most of our applications in this course, we will not be having the G vector, because we will be mostly dealing with the 3 degree of freedom systems. Now, the right-hand side tau, which was there before, we have kind of separated it out into 3 different pieces. One piece is due to the wind. So this is the external forcing on the vessel due to the wind. Then you have external forcing on the vessel due to the wave. And then this tau here represents the control impulse. So which means that suppose I have thrusters to be able to control. If I wanted to apply a certain thrust in certain direction, I'll be able to achieve that through these control inputs. So this is basically telling what my operator can control. So these are controlled by the operator. Okay, so that is the most generic form of the equations of motion, and we'll kind of try to take one term at a time and talk about it. So first, let us talk about the added mass matrix and the corresponding Coriolis matrix coming from the added mass. Now, those of you who have taken my course on maneuvering and control of marine vehicles are familiar with this representation which you see here. But for those of you who have not, these represent partial derivatives. So for example, if I take any term here, this represents the partial derivative of the sway force with respect to r dot, or the acceleration in some sense. It's not exactly acceleration because I can't just take r dot and call it acceleration in yaw, but it is telling you what is the change in force in the sway direction. So what is the extra sway force which you experience in the sway direction, given that my body is experiencing an r dot, or it is experiencing an angular acceleration. Is that making sense? Yes, no? No, this is not making sense. What's not making sense? Anand,
Yes, sir.
what's not making sense?
I'm trying to figure out after this slide what happened
You're trying to figure out what happened.
in this slide, sir. When you show this matrix.
Correct. I'm talking about the so-called added mass matrix here. So this is simply my added mass. So this multiplied by my acceleration should give me the so-called inertia force due to added mass.
Yes, sir.
So if I take, and if I'm taking this sort of a matrix, and if I'm multiplying it, say with the velocity vector, so that will be u dot, derivative of the velocity vector, v dot, w dot, p dot, q dot, and r dot. When I do this multiplication, what am I getting? Xu dot times u dot, correct?
Yes, sir.
Plus xv dot times v dot, plus xw dot times w dot, xp dot times p dot, xq dot times q dot, and xr dot times r dot.
Yes, sir.
Now, when I multiply this with the mass, with the acceleration, so this represents the added mass, right? I'm multiplying that by the accelerations. Okay, notional acceleration. This is not the exact accelerations because this is expressed in body fixed frame, and we know that we need to convert them into the GCS to get the actual accelerations. But nevertheless, the idea is that the mass times acceleration will be the force, right?
Yes, sir.
So that force, the inertial force, due to the fluid which is moving with the body, as the body is moving, we are trying to capture that part of the dynamics here.
Yes, sir.
Okay, so what I'm having as the components of these are nothing but, you remember our total force vector was given as x, y, z, k, m, and n, where the first three were the forces in a surge, sway, and surge, sway, and heave. The last three were moments about roll, pitch, and yaw.
Yes, sir.
Right? So I'm saying that when I am writing this thing, this first, let's say, coefficient, this represents nothing but the rate of change of x, which is the force in x, with respect to the acceleration in surge.
Yes, sir.
Not making sense?
So we get the mass.
Correct. So it's an expression for the mass. So if I'm saying that the inertia force due to the fluid is a function of u dot, v dot, r dot, or let's say w dot, e dot, q dot, r dot, then I can write this as a Taylor series expansion as the value when these accelerations are 0 plus del x by del u dot times u dot plus del x by del v dot times v dot, and so on and so forth, isn't it?
Yes, sir.
We know that when there is no acceleration, this force will be 0, right? When the body is not moving, there's no added mass force which is coming into the picture.
Yes, sir.
But if it is moving, then I can approximate this total force as something times u dot, something times v dot, and so on and so forth. And what this something is, it's nothing but the mass. I'm just denoting that partial derivative like this notation, that's all. I'm saying that if I write y v dot, it represents partial derivative of y with respect to v dot. Is that making sense?
Yes, sir.
For everybody?
Yes, sir.
Yes? Okay. This is not very complicated. All I am doing is that added mass times acceleration is my force. I'm just putting the notation here that this added mass basically is expressed as some derivative of the force with respect to the acceleration. So it's as if instead of writing mass, I'm just saying that that mass is force divided by acceleration of sorts. So it's still the Newton's second law, but just rearranged in a different format. So instead of writing mass, I'm writing force by acceleration. And that is signified as the derivative here. Okay, so in general,
Sir, I have a doubt.
yes.
Sir, in the previous equation, that hydrostatic force which you have talked about, you told that we don't generally talk about this hydrostatic force in ships, but the ship also has the ballast and those have loaded and unloaded conditions also. So these forces may change in that condition because of the buoyancy may also change. So
Yes, they can
I have
change. They can definitely change. But here our objective is mostly in the surge, sway, and yaw for surface vessels. When we're dealing with surface vessels, they're still going to be floating, isn't it?
yes sir.
And we will not be changing the ballast during the operation typically. Or at least that will not be the significant portion of what we want to figure out. We want to ensure that our vessel stays in some position and stays in some orientation. That is our interest in dynamic positioning, isn't it?
Yes sir.
So in that case, we are not really bothered about whether it is rolling by 2 degrees or whether it is pitching by 1 or 2 degrees. That's really not a big concern. But if the vessel moves away by 5 meters, then the crane operator really has to figure out where is my crane point and why the ship is not in the position where I wanted it to be.
Okay.
Right? So it's more to do with the horizontal modes of motion when we are talking about dynamic positioning. See, what is dynamic positioning? It is telling us that I want a certain vehicle to be at a certain location and a certain orientation, or I want it to follow a certain path that I have given it so that it executes as close to the path as possible.
Yes sir.
So here we are mostly dealing with our interest is in the horizontal modes. And in the horizontal modes, we will not have much going on with respect to the hydrostatics, isn't it?
Yes sir.
So that is why we are able to neglect it when we only have a 3 degree of freedom model. But suppose I say roll is also important to me. Okay. So now I have a 4 degree of freedom system where I have surge, sway, roll, and then yaw. Then can I assume G to be 0?
Will be considered.
I can't assume, right? I have to figure out what is going on in roll. So I have to look at the metacentric height, I have to pull that thing into the G matrix, and then I have to put it into place.
Okay.
Okay?
Yes
Did
sir.
that answer your question?
Yes sir.
Still some confusion left?
No sir, I don't think so.
Okay, all right. Any other queries, something which you would like to get explained again? Now is the time to ask. Everything clear so far? I'm somehow not hearing a resounding yes from your side.
Yes, sir.
It's clear. Everybody.
Yes, sir.
Yes, sir.
Yes sir.
Okay, all right. Okay, so now that we know that there is an added mass matrix, one of the biggest challenges for us is to go back and figure out what is that corresponding Coriolis matrix. This fellow. We had a good expression for this Coriolis matrix in terms of the for the rigid body mass matrix. We saw the expressions for these previously. But how to find out the so-called expressions for the added mass matrix related Coriolis matrix? And that's what we are going to talk about today. Okay, and the idea is pretty simple. We will derive something based on of our knowledge from the rigid body mass matrix. We saw that the Coriolis matrix can be parametrized in terms of the mass matrix in multiple ways in the last classes. You remember there were 4 different representations which we were looking at, right? If I took any one of those representations, I can actually observe that this Coriolis matrix actually is zeros in the 3 cross 3 first submatrix. The second portion of the submatrices are actually nothing but they're parameterized in terms of the mass matrix. So if I closely observe at and look at what are the terms there, I can see that it is this operation constructing a skew-symmetric matrix out of this product M11 times V1 plus M12 times V2, and that vector which I get, if I take a skew-symmetric matrix of that, that is what I was getting previously here in that so-called big terms which we were seeing there. So if I have a mass matrix which is given by 4 submatrices, 3 cross 3 submatrices, M11, M12, M21, M22, it is not very hard to see that if I perform this operation, take a skew-symmetric matrix constructed out of this vector, take a skew-symmetric matrix constructed out of this vector, take a skew-symmetric matrix constructed out of this vector, and put them all together, what I get here is actually the same Coriolis matrix which you saw in your representation 1 or representation 2. I think it's actually representation 2. Wrong. So you can actually try this out yourself if you want to try it out in the symbolic math lab part, where you can write out your entire mass matrix in terms of the inertia terms as well as in terms of the position of the center of gravity and the mass of the vehicle, and see that the Coriolis matrix which you got, which you had as CRP, we looked at the expressions for this, right? That was nothing but if I do this operation, I get that same matrix. Okay. Now I'm telling you this, but I encourage you to go back and try it out yourself if you're not convinced. So the idea of what we are seeing here is that the so-called centripetal and Coriolis matrix, the inside terms can actually be expressed in terms of the parameters in the mass matrix. Is everybody following me here?
Yes, sir.
Yes.
Okay. So it is as if that if I know the mass matrix, I can formulate the Coriolis matrix from the mass matrix using this expression.
Yes, yes, sir.
Yes. Now, we saw that for the rigid body dynamics, and the idea is that if there is a more general result, that any mass matrix, as long as I know it, I can always formulate the so-called Coriolis matrix corresponding to that mass matrix using this expression which you are seeing here. So it not only applies to the rigid body mass matrix, it also applies to the added mass matrix. And based on that, we are going to formulate what is our added mass matrix, which we will represent as CA. And we'll do the same approach, that we will take our added mass matrix, structure it into a 3 cross 3 submatrices, and then in terms of that, we'll parameterize what is the value of CA. So, in case if our mass matrix, the added mass matrix is given by a submatrices A11, A12, A21, and A22, it can be seen that we are applying the same formulation in order to get our Coriolis matrix due to the added mass matrix. Is this making sense?
Yes, sir.
Yes, sir.
Yes? All right.
It is, sir. Yeah.
Okay. Good. Now, if I do that substitution and I try to expand this entire expressions for this Coriolis matrix, you'll find that it comes out to be a matrix which has a 3 cross 3 sub-zeros and something else is happening here, something else is happening here, and you'll see that these 4 chunks, the other 3 chunks, are skew-symmetric matrices, which we expect it to be, right? Because they are actually skew-symmetric matrices. Everybody with me so far?
Yeah.
Now, what is there in these terms? That is tricky. So if I look at what is coming in these terms, A1, A2, and A3, which are coming here and here, and B1, B2, and B3, which are coming here. If I look at them, you'll see that they are related to your added masses and the variables U, V, W, P, Q, R. So A1 here will be XU dot times U plus XV dot times V plus XW dot times W, so on and so forth. So how is this coming about? Why is this particular relationship coming about? It is coming about because I am doing this operation A11 V1 plus A12 V2. Remember that if I want to expand this out, A11 V1, A12 V2, let's see what happens. So this is my added mass matrix. So I'm taking this matrix A11 times V1, which is UVW, and A12, this is this matrix, times V2, which is PQ and R. So let me see what comes out here, just to quickly understand. So I have XU dot, XV dot, XW dot, YU dot, YV dot, YW dot, ZU dot, ZV dot, ZW dot. This is A11 multiplied by V1, which is U, V, and W, plus I have XP dot, XQ dot, and XR dot, YP dot, YQ dot, YR dot, ZP dot, ZQ dot, ZR dot. And this is multiplied by P, Q, and R. This is A12, right? This is V1, this is V2. If I add this up, that is that so-called this matrix here, right? Everybody with me so far?
Yes.
Right. So what do I get when I multiply this matrix out? I should get a vector out, right? What will be the first term of that vector? So it will be a 3 cross 1 vector. It will be XU dot times U plus XV dot times V plus XW dot times W, XP dot times P, XQ dot times Q, plus XR dot times R. Similar expressions will follow for Y and Z, correct? Is this making sense?
Yes, sir.
Yes, sir.
Okay, this is nothing but your so-called A1, A2, A3. I have to form a skew-symmetric matrix out of this fellow. Yes.
Yes, sir.
Yes, sir.
So that is why you are seeing these original terms. A1 is XU dot times U plus XV dot times V, XW dot times W, so on and so forth. That is where it is coming from, because of that matrix multiplication of A11 times V1 plus A12 times V2. And once I get that vector, whose components are A1, A2, and A3, I'm forming a skew symmetric matrix out of it and putting it here. So you're able to appreciate that this expression which we have with such long expressions for each of the terms is nothing but it is representing the same thing as here.
Yes.
Yes? Okay, excellent. Okay, so that tells us how to construct the so-called Coriolis matrices for the added mass. So if I look back at my equations of motion, so now we are more confident that how to incorporate the added mass into the dynamics. So it was previously included on the right hand side into the forces, but I have now had an explicit expression for the added mass. But again, there will be a Coriolis matrix corresponding to that added mass as well. And we know that that also can be obtained if I know what is the added mass matrix itself. So if I know the added mass matrix, I can also formulate this Coriolis matrix using the parametric definition that we saw. Everybody with me so far? Good. So now we are going to next.
Sir, just
Yeah.
wanted to confirm the dimensions of the CA into V term. It must be the force, right, in newtons.
This
CA
whole, yeah, this whole thing, if it is 6 degree of freedom, CAV into V will be a 6 cross 1 vector. But if I'm dealing with horizontal modes, it should be a 3 cross 1 vector.
Yeah, the dimension I mean unit. Sorry, unit. It must be newtons.
The entire product should be in newtons.
Yeah.
Not exactly, because the first 3 terms represent the force, the next 3 terms represent the moment, right?
Yes. Yes.
So the first 3 terms of the vector will be force, which will be in newtons. The last 3 will be Newton meters.
Yeah. So can you go down a bit where xu dot into u that is calculated?
Yes.
So this xu dot into u, and that will be multiplied by u.
Correct.
That will be force.
Correct.
Xu dot is the mass, right? Added mass.
Xu dot is the so-called mass. Correct.
So that mass into velocity u into velocity u.
It won't get multiplied with u. Actually, if you look back here, where is this? Let me see here. So we are talking about this term here, right? It is part of A1, and A1 comes here, which means this thing is getting multiplied with what? It is getting multiplied with R.
Okay. Yeah.
Right? So you have xu dot times u times R.
So that will be
Mass
angular
velocity into per second.
Yes. Yeah.
So dimensionally that would become a force.
Yeah. Oh.
Okay.
Yes.
Similarly, if I see this term also, this thing is getting multiplied by q.
By q, yes.
Again, the same dimensionality applies, that it will become a force.
Yeah.
Let's say, for example, any of the B terms, let's say B11 I'm worried about. Okay?
Okay.
So B1 here is getting multiplied by R.
Yes.
Right? So I have KU dot times U times R.
Yeah. So that will be force only.
That will be moment.
Oh, sorry. Yeah. Moment. Yeah. Moment.
Yeah, because this is derivative of moment with respect to acceleration.
Moment. Yes.
Okay, so dimensionally you should get that as the moment.
Yes.
Everybody with me so far? Good question. All right. Excellent. Okay, so that is how we'll parameterize the so-called Coriolis mass matrix for the added mass. So let me come back here. So we have covered. So let's see what we have covered. We know what to do with this. We know what to do with this. We know what to do with this. And we also know what to do with this. Next, we'll talk about the so-called dissipative forces or the damping forces, and we'll try to understand what's going on there with them. Okay. So the equation of motion which I had before, I'm going to rewrite it in a slightly different form. So instead of having mass plus added mass, I'm going to simply define a mass matrix M, which is a sum of MRB plus MA. Similarly, I'm going to define a Coriolis matrix, which is simply the sum of the Coriolis matrix due to the rigid body plus the Coriolis matrix due to the added mass. So my equation of motion kind of simplifies a little bit in terms of notation. It's not simplified in terms of the physics it captures, but at least in the notation term, I don't have two matrices. I'm representing it as a single matrix now. So some mass matrix which combines the total mass plus the added mass times V dot plus the Coriolis matrix times V plus the damping matrix times V plus hydrostatics is equal to my external forces. Only thing you will notice here is that the slight change is that I'm using the notation VR instead of V. And by doing that, what I'm trying to capture is, I'm trying to see that if there are any currents in the system, then I'm looking at a relative velocity due to the current rather than a relative velocity, absolute relative velocity. I'm looking at the relative velocity with respect to the currents. And since I know that there is a representation of the Coriolis force which does not depend on the linear velocity. We saw that in a previous class, remember, where we tried to parameterize this fellow in such a way that the linear velocity actually doesn't affect it.
Yes, sir.
Yes, sir. Right? So therefore, I can get away with the fact that I can pass the same velocity vector into the Coriolis matrix in its construction, and I multiply that with this velocity vector, I should still be fine. So only difference here is I'm accounting for the so-called ocean currents also into this dynamics. Okay, so before we move on to the dissipative forces, let me just quickly cover added mass for the surface vehicles. Typically, we will find that the surge mode is usually decoupled from the sway and the yaw modes. Because of the symmetry of the vessel, you'll find that even the added mass in surge really does not affect the added mass in sway. So you can kind of make a simpler approximation of this MA when you're dealing with a 3 degree of freedom system, that you have XU dot, YV dot, YR dot, NV dot, and NR dot. Notice how we have zeros located here, indicating that the surge mode will not really affect the sway and the yaw. Is that making sense?
Yes, sir.
Right? If I move my ship or accelerate my ship in the surge direction, I don't expect to generally see a force coming in the sway direction, even an inertial force for that matter, because of the symmetry about the center line. That is why we are able to make this assumption. I hope everybody is with me on this. Yes?
Yes, sir.
Yeah. Okay.
Yeah. Typically, you will find that these cross derivatives, NV dot and YR dot, they are smaller values, and these values will be typically be seen for most ships. They'll be of comparable magnitude. They'll be approximately equal to each other. Yes, you'll find some asymmetry between them. They need not exactly be equal theoretically, but for most practical purposes, you will see that these values do not deviate significantly from each other. Now, in a 3 degree of freedom model, if this is our added mass matrix we can construct our Coriolis matrix, and a 3 cross 3 Coriolis matrix is shown here. And you can see that when I multiply that, the added mass Coriolis matrix times the velocity, I come up with these terms in the so-called inertial force. This is what turns out to be yv dot times v times r plus yr dot times r square. That is the force coming in the inertial force in the surge direction, minus xu dot times ur times r. That is the force coming in the sway direction, and this is the expression for the moment which is coming in the yaw direction. Now, if you closely observe, there is this so-called quantity xu dot minus yb dot, and this is known as the cause for a destabilizing effects, especially in aerodynamics. You'll see that for aircrafts and other things, these monk moments can be destabilizing in nature. So for certain ship types also, they can have a destabilizing effect. But for our purposes, this is not going to be relevant. It is more of a course on ship dynamics and hydrodynamics, which should talk more about this monk moment. For our purposes, we will just understand that this term is called a monk moment. We'll not get into the details of how it is destabilizing. You can look at standard textbooks in order to do that, but it won't be important for our course that we are covering on dynamic position. So with that, I'm going to stop here for now, and next class we are going to look at so-called added mass for underwater vehicles, and then we'll move on to the dissipative forces or the damping forces. Any questions so far?
Sir,
Yes.
Sir, I don't understand physically what is meant by coupling of two modes of motions. So physically, how do they?
Okay, so say suppose I am having a term here. What does this term represent? It represents the so-called inertial force which will occur in sway due to a movement of the vessel in yaw.
Yes, yeah.
Right? Which means that if I yaw my vessel, there will not only be a moment generated, but there will also be a force generated, and that force is the sway force.
Okay.
So imagine that I have my ship and it suddenly tries to accelerate about a origin's body fixed frames axis. It tries to accelerate in this direction. So if you're seeing my picture, maybe that should.
Yeah. Yes.
Yeah. So if it suddenly tries to rotate, there will be a counter moment from the fluid, which will try to stop it from going.
Okay. Yeah.
Right?
Yes.
Now that just need not be a moment, it may actually be a force plus a moment, right?
Yes.
And in which case that force is nothing but a sway force.
Yeah. Yes.
But it is coming about because I yawed the ship.
Okay.
So that is the so-called coupling. Whereas if I take the vessel and I push it forward, do I expect to see a rotation moment?
In that case, yeah, it will not be there.
Correct, right? There is no expected rotation moment. So that's why you will see that coupling term.
So that wire dot, that term is coming up only because of because the ship is not symmetric.
It is
Means,
not symmetric about the fore and aft.
yeah, that's why that wire dot term and NR dot term is coming.
Is coming.
If that ship was totally symmetric, sorry, NV dot. If the ship was totally symmetric, then that term should be 0.
Correct. You would expect those values to be 0.
Yes.
Right? But it also depends on something else, Aditya. Here is where one has to be careful. Even though the ship may be symmetric, but if I don't choose my origin at the symmetry location,
Okay.
then too I may get a coupling.
The force.
Because suppose if the ship is symmetric, and you were right that if I put my origin at the symmetry point or the origin about which it is symmetric, then if I rotate the ship, I should not expect to see any sway force.
Yeah.
But if my origin is shifted to the front of the ship, let's say,
Yes.
now can I say that there is no force acting at this point? It has to have a force in order to take the total moment to be zero about the origin.
Yeah. Yes. Yes.
So it's not just a question of what you call whether the body is symmetric or not, but it also depends on where we choose our coordinate frame. That also will cause coupling to come.
Yeah. Yes.
Good question. Any other queries?
So then there might also be a very small contribution in XR dot also, right?
There may be a small contribution in XR dot also. Yes, it possibly can be a small contribution in XR dot also. But we typically find that these values are much smaller, even smaller than what you would see in NV dot or YR dot.
Mm.
Yeah.
Okay.
Mm.
But you are right. XR dot need not be zero, although you can kind of argue that NX, sorry, yeah, NX dot, NU dot would be zero,
Mm.
right? Because if I suddenly increase the speed of the ship or
That will not cause anything.
I don't expect to see a moment come about. So you can already kind of get the feel for the idea when I said that the added mass matrix need not be exactly symmetric, but you will find that for most purposes it is approximately symmetric.
Mm.
Yeah.
All right, any other questions? Good questions you're asking. Okay, if there are no other questions, let me stop recording now.